Thanks for tuning in to this revision zone video. This is part 2 of the energetics topic, and we're looking at using the calculation Q equals mc delta T and measuring enthalpy changes. So let's get right to it. So measuring energy changes experimentally. Now, when we look at this, we need to think about, well, like we looked at in a previous video, a reaction can either release energy or absorb energy into the system. Now, if it releases energy, then we know that is exothermic. And if it absorbs, we know it is endothermic. Now we need a way of measuring these energy changes. Now what we do know with exothermic, that the temperature change will increase, and for endo it's vice versa, it will go down. Now a change in temperature indicates that either energy is being released or being absorbed. It doesn't tell us exactly how much energy is being released directly, but it gives us, or absorbed, but it gives us an idea or an indication that there is a transfer of energy. So we need a relationship between temperature and the energy to be able to give us the energy released or absorbed during a reaction. Now that relationship comes from Q equals mc delta T. So we're going to just deconstruct this equation. You will have come across this quite a few times, even at GCSE and even within physics. Now, in chemistry, there are a few changes we need to make. So it's slightly different to physics because instead of kilograms, we use grams instead. So it's definitely worth keeping that in mind if you do A-level physics, is not to confuse the two. So Q can sometimes see it as E. This is just measured in joules. There are no signs for this part of the equation. So I'm not looking for a plus or negative, and I'll come back to that later on. M is mass. Now this is the mass of whatever you are taking the temperature change of. And that is typically, most of the time, it is water, and it's measured in grams. You are usually putting your thermometer in water or a solution, which is majority water. So that will be measured in grams. And again, we'll come back to that when we're looking at questions. C is the specific heat capacity. You do need to know or need to have an understanding of what specific heat capacity actually means. Now, specific heat capacity, before we do go into looking what the definition is, we'll just write the units: joules per gram per Kelvin. Or what we can use here is joules per gram per degree Celsius. It doesn't matter which unit of temperature we actually use here, because we are not measuring a specific temperature, or we're not using a specific temperature in this calculation. We are more interested in the change in temperature. And so therefore that can be measured in degrees Celsius or Kelvin. Now going back to specific heat capacity, if we look at the definition, it says joules per gram per Kelvin, so the unit, sorry. It's basically a measure of how much energy is it required to move 1 gram of substance up by 1 degree Celsius or 1 Kelvin. So if this was 1 gram of substance, shade that in, that's 1 gram substance. How much energy does it require to get that 1 gram of substance up by 1 degree Celsius or 1 Kelvin? One thing I will say, a lot of people think, oh, metals are good conductors of heat, which they are, so they must have high specific heat capacities. Well, actually, because they're so good at conducting, they have very low specific heat capacity, so it doesn't take much energy to raise it through a certain amount of degrees Celsius or Kelvin. So just keep that in mind. Typically in this case, we use 4.18 joules per gram per Kelvin. I'm just going to stick to Kelvin because it is the SI unit, and this is of water. Now, the reason I'm stating this is because most of the time your thermometer is in a solution which is made up of majority water, or it's in just water in a calorimeter. Now, so please do learn this, please do know this, but if they do quote a value for the specific heat capacity in a question, always use that particular value. So just again, looking into this a little bit further, how do we actually measure this value experimentally? Well, in order to measure this value, we need to know this. We need to know the change in temperature. And in order to make an accurate measurement of change in temperature, we need to use something called a calorimeter. Now, a calorimeter is just a device which helps us measure the temperature change in a reaction accurately. And they might be as simple as a polystyrene cup. Okay, and we use polystyrene because polystyrene is a good insulator, so it reduces heat loss. I'm just going to do that again. And we use a lid to reduce heat loss. In that lid, we might poke two holes, one for a thermometer and one for a stirrer. This is my stirrer here. Now the stirrer is not probably, but it will be used to get a uniform distribution of energy through the water, so you get a good temperature change or measure of temperature change. Thermometer is obviously there to measure the temperature change. Now, to improve this and for stability as well, we can put it in a glass beaker. So here's my glass beaker, and what my glass beaker will do is it will trap air around my polystyrene cup calorimeter, and we know air is a good insulator, so that reduces heat loss even further. So this is my calorimeter. Now, depending on what type of reaction we're doing, this calorimeter may change, and we will look at better calorimeters in another video, but this is your bog standard, your basic calorimeter. If I'm doing reactions in solution, then it will be this type of calorimeter. However, if I'm trying to measure the amount of energy released from a fuel, I would use a copper cup calorimeter, and we'll look at one of those calculations later on. But we use a copper cup calorimeter because copper is a good conductor of heat, and it will absorb as much of that heat as possible from that flame. So this is the kind of apparatus we will use. What we also need to consider is that one of our components in a reaction will always be in excess. And we must consider that that is actually the value we're not interested in. We're not worried about the number of moles of the substance in excess. It's the one that's limited, the one that we don't have a lot of, or the one that will stop the reaction first because it will run out first. So once we've got Q, so if we come back to the top here, once we've got Q, we need to now use that value Q, the energy change. Now this is either called energy change or energy transfer. I'm going to call it an energy change, but just be mindful of those two. Do not confuse it with enthalpy change. If in the question it says energy change or energy transfer, it is referring to calculating Q, nothing else. Let's have a look at calculating enthalpy changes. Now I'm just going to write Q equals mc delta T here again, because we need to use Q here. Now Q is the energy transfer as mentioned above, and that's going to be measured in joules. Now I want to work out the enthalpy change for reaction. Now the enthalpy change is normally measured in joules per mole. This is the SI unit for enthalpy change. So we do need to do something with joules first. We do need to convert it to kilojoules. You can do this at the end as well. But a lot of students decide to divide by 1,000 here to get it into kilojoules. Now, the way we work out the enthalpy change, well, as the units state here, it's the energy divided by the number of moles. So we need to calculate the number of moles, which means that the enthalpy change is Q divided by moles. Now, like I said, you can change Q into kilojoules straight away, or you can do it at the end. But if we want to just stick to what we said earlier, we want that to be in kilojoules. There is no sign for Q, and neither should you state a sign for Q. There is no direction of which way that energy transfer we would have worked out in the first stage, Q equals mc delta T, is going. And we don't want to state that direction there. It is just a value, nothing else. So in this particular case, what we'll look at the end is deciding whether it's ex or endothermic. But first, we need to look at where we get that number of moles from. Now, that number of moles comes from the limiting factor. This is the limiting factor now, or reagent. So whichever reagent is not in excess. So basically, the one that's not in excess is the one that we use for this part of the calculation. Q, we will obviously have from Q equals mc delta T. When we work that out, we should get an enthalpy change in the unit of kilojoules per mole. Now, what we do need to decide at this point is that whether it's positive or negative. It's at this point you need to decide or go back and have a look at what my delta T was. Was it a rise? If it was a rise, then my enthalpy change is exothermic, therefore it is negative. Was it a decrease? If it was a decrease, then delta H will be positive because it's endothermic, and that's the only time we put sign in. It is very important that you even put a plus sign in if it's positive, and I will mention this in other videos. But so if it's plus 201, let's say kilojoules per mole, then you need to put that plus in. Minus, obviously you need the minus, a bit more obvious to students, that one, but sometimes the plus is not so obvious. These two signs here give us a direction, and that's really, really important to know whether it's endo or exothermic. Don't make the assumption just because you don't put a sign there it's positive. It's not necessarily the assumption that we make within chemistry. So what we're going to have to do is, and we will have to look at some assumptions, and I'll do this as we look through some example questions. We need to try and apply Q equals mc delta T and calculate the enthalpy of reaction. Now, the first one I'm going to look at here is the enthalpy of a reaction that takes place within a solution or within water, and therefore we are going to use our polystyrene cup calorimeter. Now, in order to apply this particular scenario to Q equals mc delta T, we do need to make a few assumptions first. Now, any solution that we have within our polystyrene cup calorimeter, and I have a diagram of that on the right hand side here, we'll have a solution in here. In this particular case, we know that that we have 3 moles per decimeter cubed of hydrochloric acid here, 50 centimeters cubed of that too. That's in there. So we've got 50 centimeters cubed of HCl at 3 moles per decimeter cubed. We need to make a few assumptions about this. Now, one is that the amount of HCl inside the water that is dissolved in, the HCl does not affect, so it does not affect the overall density of water. It does in reality, but to make our life simpler, we want to make that assumption. It also does not add to the mass, therefore. So therefore, does not change the mass. Now you might be thinking, well, of course it does. We've added some stuff to water. The solute will have a mass, and conservation of mass means that the mass won't be the same as just water or as it was before. You're absolutely right. But in order to make our life a little bit more simpler, there's no real gain by doing all those additional calculations. In terms of accuracy, we just decide to leave it out. So that means that if the density of water is unchanged, that means that the density of water is 1 gram per centimeter cubed. It's unchanged. So for every 1 centimeter cubed, it's 1 gram. If I have a 50 centimeter cube solution of anything, and that doesn't mean it's limited to HCl, obviously. It could be copper sulfate, it could be any kind of solution of sulfuric acid, sodium hydroxide. We assume that the mass is equal to 50 grams. And that's also taken into account this assumption here, that the mass of the solute doesn't affect the overall mass of my solution. And again, to make our life a little bit more simpler. So I don't want to go and work out the mass of HCl, which is a common mistake, and then add it to the 50 grams and then put that into my calculation. I really don't want to do that. So now that we've done that, we can actually look at the calculations. Now, I'm going to start by writing Q equals MC delta T. Now, I always advise that you read through the question and underline the key parts in the question. So we'll quickly do that. So we've got excess solid magnesium oxide added to 50 centimeters cubed of 3 moles per decimeter cubed HCl, which we've already aligned. The initial temperature of the solution was 21 degrees Celsius. After the reaction has taken place, the temperature has risen to 53 degrees Celsius. So straight away in your mind, you should be thinking, oh, I've got delta T there, got a change in temperature. And they've given the specific heat capacity, even though I quoted that at 4.18 joules per Kelvin per gram in this case, or joules per gram per Kelvin. It doesn't matter how you state the latter two units there. I am going to use what they've given in the question. So I'm going to use this information to calculate the enthalpy change of the reaction for 1 mole of magnesium oxide with hydrochloric acid. For your calculation, you should assume that all the heat from the reaction is used to raise the temperature of 50 grams of water. A couple of things there. We're assuming no heat loss. So we're assuming that we've done everything we need to do to make sure we don't lose any energy. Obviously not the case and not true, but in these calculations, we have to assume that. So I do need to put some additions to this diagram. I need a lid to reduce that heat loss. I'll need a stirrer, dodgy looking stirrer there. And I've got my beaker to trap that air for additional insulation. Now, I need to now calculate Q. That is something I can do straight away. So I've written my equation, always like to do that to begin with. Shows the examiner what equation I'm using and how I'm displaying my calculation. My mass is 50 grams. It's been mentioned here that 50 grams, and it's been mentioned here but as centimeters cubed, but I know it is 50 grams due to our assumptions down below here. And also make sure you remember from what I said before, the thermometer, whatever you measure the temperature of using your thermometer, or whatever your thermometer is submerged in, that will be the mass that you input here, nothing else. Don't put the mass of anything else here. That's really quite important. So the mass here is 50 grams. And my specific heat capacity as given above, 4.2 joules per gram per Kelvin. My temperature change here is 32 degrees Celsius because it's going from 21 to 53 degrees Celsius, but I'm going to add in Kelvin. So I've got Kelvin here. The temperature change in Kelvin and degrees Celsius will always be the same. That gives me a value of 6,720 joules. You have a choice here. You could convert that to kilojoules here, or you could just do it later, but probably advisable just be in the habit of converting to kilojoules to begin with. And now I want to use this value to work out the enthalpy change. Now my enthalpy change is my Q divided by number of moles. Now before I get onto this, just a couple of points. One, even though I know it's an increase, I haven't included a sign for my Q. I haven't put a plus there. Even if it was a decrease, if it was an endothermic reaction, I would not want to put a negative here. Just want to keep this sign out of the way. So if they ever ask you to work out the energy change, always just give it without a sign. Now I need to know, the second thing is I need to know the number of moles, and this is the number of moles of my limiting factor, of the limiting factor. Now the limiting factor is the one that's not in excess. My excess, as shown above, was the magnesium oxide. So it's actually the number of moles of my hydrochloric acid that I need to work out. So the number of moles here is my 50 centimeters cubed divided by 1,000 to get into decimeters cubed, times by my concentration is 3.0, and I end up with 0.15 moles. Now, this is the number of moles of HCl used. We cannot make the assumption that it is 1 it's equivalent to 1 mole if I use it here. Okay, so that bit there. I need to make sure I look at the equation before I input this into the calculation of enthalpy change. Now what I'm going to do is I'm going to start writing the equation just up here. So I'm going to magnesium oxide solid plus HCl aqueous gives us magnesium chloride aqueous, plus water liquid. This needs to be balanced, and that means I need 2 HCl's for every 1 magnesium oxide, which means that this is a 2-to-1 ratio. And because it's a 2-to-1 ratio, I know that my 2 parts, if you like, is equivalent to 0.15 moles. So what I need to do is I need to make this to a molar, 1 mole, if you like, a ratio. So it'll be 0.15 divided by 2, which gives me my 0.075 moles. Now, if it was with respect to magnesium oxide, I would just work out the moles of magnesium oxide and put it into here. But because that is in excess, I can't use that. I have to use the HCl. So now it's actually the 0.075 that we input into my energy change over moles, and that is let's start again, 6.72 kilojoules divided by 0.075 moles, and that gives us 90 kilojoules per mole. Now I've done it to 2 significant figures here because I've also got all my values quoted to 2 significant figures. So we now need to decide whether it's exo or endothermic. That's the final thing left for us to do. Now we know that there was a rise in temperature, so this becomes minus because it's exothermic, and we need to make sure we put our sign in there. Even if it's positive, we need to put our plus in. So that concludes how to calculate the enthalpy change of reaction when we're looking at solutions. These assumptions to the right are really important that you incorporate because they're common mistakes that students forget about and therefore introduce error into their questions. So we're going to have a look at our next question, which involves the enthalpy of combustion. So a slightly different method to calculate the enthalpy, not using a polystyrene cup calorimeter. So this is the question that we are going to look at for enthalpy of combustions. Now I'm just going to quickly read through the question prior to us actually making a start. So this is an experiment that was conducted to determine the enthalpy of combustion. Now the enthalpy of combustion is something that we'll cover in later videos, but it will refer to 1 mole of substance. So we need to make sure we are only combusting 1 mole of liquid methanol. The energy obtained from burning 2.12 grams, and that's going to be useful for us to calculate the number of moles because this will be the limiting factor, okay, of methanol, was used to heat 150 grams of water. Now that could be 150 centimeters cubed instead of 150 grams, but made your life a little bit easier by putting 150 grams in. The temperature of the water rose, so that tells me it's exothermic, from 298 to 362 Kelvin. Now, it doesn't matter if it's degrees of Celsius or Kelvin either. And they've quoted our specific heat capacity of water as 4.18 this time. So that's the value we will use. Now, to the right quickly, we can see that I have 2 diagrams. This is basically a very simplified diagram of a copper cup calorimeter. So you've got your copper can, you've got your thermometer. I would want a lid over that with a stirrer. That's supposed to be my stirrer, and I've got a diagram underneath that which shows an actual copper cup calorimeter. We've got a stirrer here, and we've got our copper can. Now that's either clamped or on a gauze or something to suspend it over the flame, and we want that as close to the flame as possible to reduce the amount of heat loss. What we have underneath is a burner or spirit burner. Now that's any fuel. In this case, for us, that is methanol. And we're going to be burning that, and we know how much we're going to burn because we've been told that in the question, in 2.12 grams. I've changed this value here. It was 200 centimeters cubed before, but I've changed it to 150 because that's what we have in our question, 150 centimeters cubed water. And it's that quantity that is being heated up. That's where I'm detecting my temperature change. That's where my thermometer is, and that's what it's detected in temperature change of. So that value there will be in my Q equals MC delta T. So worth considering all those points. Now, again, we assume that there is no heat loss, but there's plenty of heat loss here that we'll find, and we'll see in later videos how we can remove that. But one thing we could do is put draft excluders in to remove or reduce that heat loss. We could surround this with insulating material to do that too. So anyway, let's get stuck into the actual calculation. So we're going to look at Q equals MC delta T again. We need to write down what each of these values are. So my M is the mass. Now the mass is of water because that's where the temperature change is occurring. Not going to write 2.12 grams here. That is not my mass. And my thermometer is not in the burner. It is in the water. So that is what's inputted here. And please don't add 2.12 grams here because that would be incorrect too. We times that by the specific heat capacity of 4.18. And we times that by the temperature change of 64 Kelvin in this case. You can see I've put no units here. You don't really need them, but just make sure you know what the units are. That gives me an overall value of quite a large number, 40,100 joules. Now, again, we can take the step of converting that to kilojoules. So divide by 1,000. Let's write that in. And that goes to 40.1 kilojoules. No sign here. I'm not putting positive or negative there because I don't need it. Now I need to take this on to the next stage. Now, before I can work out the enthalpy change, which is given by this equation as we know, I need to work out the number of moles and my limiting factor. My limiting factor in these cases is always the fuel. It's always the fuel for combustion, because the oxygen has to be in excess to make sure we get complete combustion. I know my Q is 40.1 kilojoules, but I need to work out the number of moles of my methanol. So to work out the number of moles of my methanol, so I'm just going to continue this to the right, I know that my moles equals mass over MR. I have my mass at 2.12 grams. And my MR for methanol is as follows, 32. And that gives me an overall number of moles of 0.0633 moles. Now, just aside, I'm going to, underneath the copper calorimeter, I'm going to write the chemical equation for this. So methanol is CH3OH, liquid, plus oxygen gas, gives me carbon dioxide gas and water. I need to make sure that's balanced and that's a liquid. So I've got one carbon. I've got 4 hydrogens on the left. I need 4 hydrogens on the right, so I'm going to put 2 there. That gives me 4 oxygens on the right and only 3 oxygens on the left. So I need another oxygen here. So I need 1.5 here. So I can either go 3/2 or I can put 1.5 there instead. It's entirely up to you. But in this equation, I can see that it is at 1 mole. So therefore, I don't need to do anything to this value. I just need to quite simply add it into here, this equation. So we're going to do exactly that. So delta H is equal to my Q, 40.1 kilojoules, divided by my 0.0633 moles. And that gives me, excuse me, 605 kilojoules per mole. Now, again, I need to go back and do one final check. I've done it 3 significant figures because, again, we have 3 significant figures given in our numerical values in our question. So I can go up to 3SF. So I'll put 3SF there. But I do need to make sure I have a sign. And my sign here is going to be negative because it was a temperature rise, and we know therefore it's exothermic. So that concludes this calculation for the enthalpy of combustion and the slightly different setup, and therefore we have to do a slightly different take on the calculation, or the latter part of the calculation. But the initial part is very much the same. It's the water that you put in as the mass, the specific heat capacity of water, and the temperature change of the water. So that's always for the water there. It's a good guideline to use. So I hope this video was useful. If you enjoyed it, please hit the like button and subscribe for more videos. Use the comment section to let us know what other videos you might want to see, and we'll hopefully see you next time.